Delaware Tech, Chemistry 110, Chemical Quantities and Reactions Continued, Stoichiometry, Mass in Chemical Reactions. Stoichiometry is a method that allows us to calculate how much of a product we make or how much of a reactant we might need in a chemical reaction if we know the amount of any other substance in that chemical reaction. But before we go into the details of stoichiometry, let's review what a balanced equation means. Remember, balanced equations are fixed ratios of each of the substances, either reactants or products, in a chemical reaction. So here's a simple chemical reaction. 2 H2s plus 1 O2 produce 2 H2Os. 2 hydrogens plus 1 oxygen, these are molecules, produce 2 water molecules. And we can think of this in a number of ways. We could think of it as 2 molecules of hydrogen gas plus 1 molecule of oxygen gas produce 2 molecules of water. We can think of it as 2 moles of hydrogen plus 1 mole of oxygen produce 2 moles of water. And this is actually the most common way to think about it, but it is not the only way to think about it. The point here is that it's a fixed ratio. It doesn't matter what unit we're using. It's a 2 to 1 to 2 ratio no matter what, as long as we're using some method that counts the particles of the substances, either atoms or molecules or formula units or ions. We can have 2 times Avogadro's number worth of molecules of hydrogen. That's the same thing as a mole. Plus 1 of Avogadro's number of molecules of oxygen form 2 of Avogadro's number of molecules of water. Or we could say, we could triple everything. We could say this means that there are 6 moles of hydrogen and 3 moles of oxygen would make 6 moles of water. We could cut it in half. 1 mole of hydrogen plus a half a mole of oxygen makes 1 mole of water. It doesn't really matter what we use. We can even use really odd-looking numbers. We could say 2 of 0.0568 moles of hydrogen plus 1 of 0.0568 moles of oxygen will form 2 of 0.0568 moles of water. Whatever equivalent we want to use is fine, as long as it's some way of counting these particles. In this case, they're all molecules. So 2 equivalents of hydrogen will react with 1 equivalent of oxygen to form 2 equivalents of water. And note, when I'm saying hydrogen and oxygen, I'm talking about the molecules, the elemental form. I'm not talking about the atoms, hydrogen atom, oxygen atom. I would say atom in that case. Since these are both diatomic elements, when we say hydrogen, we mean H2. When we say oxygen, we mean O2, unless we specify otherwise. So here's another reaction. 4 aluminum metal plus 3 oxygen makes 2 aluminum oxide. Well, here are the ratios. You know the ratio of these 3 substances is a 4 to 3 to 2 ratio. That is fixed by the balancing of the equation. These are the coefficients that are fixed ratios. We know that for every 4 aluminums, we need 3 oxygens. For every 3 oxygens, we'll produce 2 aluminum oxides. For every 2 aluminum oxides, I need 4 aluminums. So any pair of these will form a known ratio. So here's another problem for you. If we know that for every 4 aluminums, you react 3 oxygens to produce 2 aluminum oxide, that's what the balanced equation says, how many moles of aluminum are needed to produce 8 moles of aluminum oxide? Well, your reaction shows 2 moles of aluminum oxide. 8 is 4 times that amount. So you can multiply 4 times every one of these numbers, and you would see you would have 16 moles of aluminum plus 12 moles of oxygen produce 8 moles of aluminum oxide. So that would be a 4-fold version of this, and that means we would need 16 moles of aluminum to make 8 moles of aluminum oxide. So the reason why this is important is this is an important concept to understand in order to determine how much material you need or will produce in any chemical reaction. If somebody asks you how many grams or how many liters of gas you're going to produce, or how many milliliters of a solution you need for a chemical reaction, in the middle of these calculations, you're going to need to convert the amount of one substance to the amount of another, and we use the balanced equation coefficients to allow us to convert moles of one of these components to the moles of any other, because these are fixed ratios. These coefficients are your ratios, and therefore they are your conversion factors to go from one substance to another, but they must be done in moles. So here's an example. Here we have a balanced equation with made-up substances. 2A plus 3B gives 4C plus 1D. So the question, how many moles of C are formed if we react 4 moles of A? Well, 4 moles of A is twice as much as the 2 moles of A, so we double everything. Well, we would have made 4 moles of C, so now we're going to make 8 moles of C. How many moles of B are reacted if we form 5 moles of D? Well, 5 moles of D is 5 times as much as this equation says, so we multiply everything by 5. And if we're interested in B, we multiply the 3B times 5. So to make 5 times as much D, we need 5 times as much B, or 15 moles. So let's look at this one. How many moles of B are reacted if we form 7.32 moles of C? Well, this is a little more complicated, isn't it? It's not a simple ratio to multiply everything by, so it's time to do some math. And how do we approach this? Well, we always start with the thing we have. And in this particular question, the thing we are told we have is 7.32 moles of C. And it doesn't really matter whether the thing we have is a product or reactant. We're given any one of the substances, we can figure out how much of any one of the other substances are either required or will be produced. It doesn't matter which one we start with, we can get any one of the others. So we start with 7.32 moles of C. And we use the fact that we know from the balanced equation that we will use 3 moles of B for every 4 moles of C produced. It's a 3 moles of B to 4 moles of C ratio. And since we're converting moles of C to moles of B, we would use this information as our conversion factor. And that would be written like this. We start with the 7.32 moles of C. We produce our conversion factor, so first make your parentheses, make your dividing line before you put anything in. And then you realize before you write 3 moles of B or 4 moles of C or anything in your conversion factor, put your units in first. You know you want moles of C on the bottom because you're destroying that unit. And you are creating the unit moles of B. So moles of B has to be on the top, moles of C is on the bottom, and then you populate it with the numbers. You've written moles of B over moles of C. Well, how many moles of B? 3 moles of B. How many moles of C? 4 moles of C. You get that right from the balanced equation. So it's important to balance your equations properly or you'll get the wrong coefficients and therefore the wrong conversion factor. And when you put this into a calculator, you find that for every 7.32 moles of C that you produce, you must have reacted 5.49 moles of B. And this will become an important step when we're doing full stoichiometry calculations shown in the next slides. So here's another practice problem for you. How many moles of A are needed to react 4.33 moles of B? And you can pause it right here. All right, and let's remember, what do? You always start with the thing you have, 4.33 moles of B. What other information do we need? Well, we're going from moles of B to moles of A. We know that for every 3 moles of B we react, we must also react 2 moles of A. So we use this information to create our formula. We start with our thing we have, 4.33 moles of B, and we build our conversion factor. We make our parentheses, we make our line. We know we want moles of B on the bottom, and we're creating moles of A, so that's on the top, and only then do we put the numbers in. We know it's 2 moles of A over 3 moles of B, and then we multiply and divide out the numbers, and we get 2.89 moles of A. Now, does that make sense? We end up with less moles of A than we started with moles of B. Well, yes. Look at the original balanced equation. For every 3 moles of B, we only need 2 moles of A. So our number should be 2/3 of our original number. 2/3 of 4.33 is, in fact, 2.89 moles of A. So it worked. So let's look at another example. So this is an example where we're going to have various amounts of moles of different substances, and we have this reaction here. Here's a reaction with C2H2. This is acetylene, as in acetylene gas. You might have known it by naming it by the old IUPAC naming method. You would have said dicarbon dihydride, but the true name for this is acetylene. So 2 acetylenes are reacting with 5 oxygens to produce 4 carbon dioxides, CO2s, and 2 H2Os, waters. So the question says, if 3.84 moles of acetylene are burned, how many moles of oxygen are also needed? Okay, well, we know for every 2 moles of acetylene, we need 5 moles of oxygen. So there's our ratio. There's our conversion factor. We start with what we know we have. We build our conversion factor. We make sure our moles of acetylene are on the bottom because we're destroying that unit, and we're creating moles of oxygen. So it's going to be moles of oxygen over moles of acetylene. Then we put our numbers in, 5 and 2. We multiply it out, and we see that we need a lot more moles of oxygen for however many moles of acetylene we have. Second question, how many moles of acetylene are needed to produce 8.95 moles of water? Start with what you have, 8.95 moles of water. We know the ratio of water moles to acetylene moles is 2 to 2. Well, it's not going to change anything. 2 over 2, those numbers cancel, and then moles of acetylene cancels with moles of acetylene, and we're left with the same number of moles, but now it's moles of oxygen. And that makes sense. The last question, if 2.47 moles of acetylene are burned, how many moles of CO2 are formed? Well, we know that for every 2 moles of acetylene, we get 4 moles of CO2, which is twice as many moles. So you could actually do this in your head. You realize you need twice as many, you're going to make twice as many moles of CO2. You can just multiply it by 2, but use the proper way. 4 moles of CO2 ratio over 2 moles of acetylene will turn your original 2.47 moles of acetylene into 4.94, or double the moles of CO2. So let's talk about what stoichiometry is before we do a full stoichiometry problem. Stoichiometry is from the Greek words meaning measuring elements, and it's pronounced stoichiometry. A lot of students stumble on this pronunciation, but just practice it a little bit and you'll get it pretty quickly. Stoichiometry. Okay, and this is basically the method of calculating how much reactants or products you will either need or will produce in a chemical reaction if somebody gives you the amount of any other reactant or product in that chemical reaction. And the amounts may be in moles, which makes things easy, but they might be in grams, or they might be in liters of gas, or they might be in liters of a solution, and you need to know the concentration of the solution. Now, we'll get into liters of gas in the next unit on gases, and we'll get into liters of solution when we do the solutions unit, but for now, we'll just worry about grams or moles, or occasionally particles, like how many molecules you have, how many formula units, how many atoms, how many ions, in actual counted numbers. And we know how to convert those. We have those conversion factors. So here's an example of a typical stoichiometry problem. If you burn 10 grams of CH4, CH4 you learned from nomenclature would be called carbon tetrahydride, but the true name for this compound is methane. This is methane gas. The gas in natural gas, that's the predominant component of natural gas. It's what you burn in your Bunsen burners in the laboratory. It's what you burn on a gas stove. If you burn 10 grams of methane, how many grams of CO2 will you make? Well, before you can even tackle this problem, we need an equation. And you know that this is a combustion reaction. It's a carbon compound that you're burning. Burning means you're reacting it with oxygen. So we need to produce a formula. And then after we do that, we can look at the formula, we can balance the equation, and we'll have the balanced equation information. But we'll also need to convert grams to moles. And we'll need to convert moles of CO2 back to grams of CO2. So that means we're going to need some molar masses. We're going to need the molar mass of methane, and we're going to need the molar mass of CO2. Anytime you see grams in a problem that says you have this many grams or you need a certain number of grams, you're going to usually need the molar mass to calculate those grams or moles from the moles or grams respectively. So be sure to get ready and calculate molar masses, because these two things, molar masses and your balanced equation, this is the source of your conversion factors that you will need to do stoichiometry or stoichiometric equations, mathematical equations. So in a simplified example, somebody might give you the grams of A in a reaction, and they say, hey, how many grams of B will I produce? Or how many grams of B do I need to react with A? Or maybe A is the product and B is the reactant. It doesn't matter. It's grams of one of the substances, and they're asking for grams of another substance. Well, how do you do that? Well, first you build your map of what you want to calculate. And you're going to start with the thing you're given. If you're given grams of A, that's what you start with. And you're going to build your your mathematical equation based on the chemical equation. So you start with grams of A, that's what you know you're going to start with, and in the end, you're going to end up with the grams of B. But how do you go from grams of A to grams of B? You can't go directly. There is no direct calculation from grams of A to B. You have to, what do you know how to convert grams of A to? Well, the only thing you know how to convert grams of A to really would be only moles of A. That's the only thing you know how to convert to. But to do that, you need the molar mass of A. So first you're going to have to figure out the molar mass of A, and you can use that as your conversion factor to get moles of A. Well, in the end of this problem, you're going to need grams of B. How do you get grams of B? Well, what do you think you're going to get grams of B from? Well, you're going to get grams of B from moles of B. And once you have moles of B, you can convert that to grams of B if you know the molar mass of B. So it's important to know the formulas of A and B in order to determine what the molar masses of A and B are, and that allows you to go from grams of one to moles of one, or moles of the second to the grams of the second. So now we know how to go from grams of A to moles of A. We know how to go from moles of B to grams of B. How do we connect these two into one big pathway to get from grams of A to grams of B? Well, we have to have some way of going from moles of A to moles of B. And anytime you're going to convert moles of one thing to moles of another thing, you are going to use the balanced equation's coefficients. Those are fixed ratios of the moles of every substance in the reaction. And that means you need to write the right equation, and you need to balance it properly to get those coefficients. And if you look at this, each of these arrows represents a conversion factor. Molar mass, balanced equation coefficients, molar mass again. Every time you see an arrow, you're going to replace it with parentheses and a conversion factor. So you could write it like this. This was pulled out of another textbook. It really says exactly what the line in blue just above it says, but it's in a little more detail. Grams of A times 1 over the molar mass. Why 1 over the molar mass? Because you want grams on the bottom, you want moles on the top of your conversion factor. So in this particular diagram, the The bluish gray are the things you start with and the things you're calculating. And you don't have to calculate all the intermediate things. You don't have to calculate moles of A and moles of B separately. You can just cram all your conversion factors against one another and multiply it all together and get your final grams of B answer. But if you stop after one conversion factor, you'll get moles of A. If you stop after the second one, you'll get moles of B. And if you stop after the third one, you'll get grams of B. So this is how you set up any stoichiometry equation where you're starting with grams of one thing and you're ending with grams of another thing. So let's talk about the handout that you were already given. This handout is a map that shows you the exact same thing. And you'll notice that I have different colored boxes. The box is in yellow in the center. This is your balanced equation coefficient conversions. It's the moles of any one thing to the moles of any other thing. And I just happen to use as an example moles of A to moles of D or vice versa, but it doesn't matter which things. It's moles of one thing to moles of another. You'll notice it also includes something called delta H. That is the heat of the reaction called enthalpy, and we'll talk about that in another module later in this unit. So you can disregard that for now. If you look on the sides of the reaction, well, first let's focus on the center again. Moles are being converted to moles. That's what happens in a chemical reaction. Chemical reactions don't care about the grams or how many they don't care about the grams or how much volume it takes up. They care about how many particles, and we count particles in moles. So everything has to be done in moles. Well, you're not always given moles. You're given grams. You're given volume in liters or volumes of solutions in milliliters or liters. You need to convert that to moles. Now, you'll notice in blue, it says volume in liters of gas. We cover that in another unit, in the gas unit. And in violet here, we've got volume of liters of solution. That will cover in a unit even later than that. That'll be the solutions unit. So let's just disregard those for now, and you can disregard the bottom part of this yellow box. So for this unit, you need to be able to go from grams up in the upper left-hand corner of one substance or particles of that substance using Avogadro's number instead of molar mass to get moles of the substance. And once you have the moles of one substance, you can use the balanced equation to get the moles of any other substance. Once you have the moles of any other substance, you can convert that to grams or to particles. It could be the number of molecules, or the number of particles means number of atoms or number of molecules or number of formula units or even number of ions. It's just any kind of particle. So when you see the word particle, it means any of the smallest unit of that particular substance. So this is your overall pathway. You're going to go from grams or particles to moles. You need to get to moles. You can convert moles of one thing to moles of another thing, and then you come out of the yellow box and turn it into what you want in the end. And that's usually going to be grams, but occasionally it might be particles.